All right, in this segment, we're going to be introducing an important new concept, the idea of free energy, and we'll see how it relates a lot to what we've already looked at in terms of enthalpy and entropy. So the objectives for this lecture are state and understand the consequences of the three laws of thermodynamics, understand the relationship between the enthalpy of the system and the entropy of the surroundings, and finally understand how Gibbs free energy keeps track of the entropy of the universe as a whole. Okay, so let's go back and restate the second law of thermodynamics again. That not only can't you win, you can't break even, right? The first law is you can't win, energy is conserved. The second law is you can't break even. And what does that mean? So reactions proceed spontaneously in the direction that increases the entropy of the system plus the surroundings, or that the entropy of the universe increases. Whatever you do, whatever process you undergo, besides conserving energy, it will also increase the entropy. So you can't keep the universe in the same state it was. It's going to change states towards states with more entropy. And so again, we say that a spontaneous process proceeds on its own without any continuous external influence. We can certainly get non-spontaneous things happening, right? We talked how iron corrodes into iron oxide spontaneously, but with the application of electrical current, you can cause that reaction to be reversed. So, but you have to put in external influence in order to drive it. You can couple reactions together. You can take one spontaneous reaction and connect it to one that's non-spontaneous and end up with a spontaneous reaction overall. So non-spontaneous, yes, process is one that takes place only in the presence of a continuous external influence, a reaction that only goes in the reverse direction if you force it in some way. Okay, so second law, the total entropy of an isolated system never decreases, but a better way to state it is in any spontaneous process, the total entropy of the system plus the surroundings always increases. That the universe, the entropy of the universe, which is really just the entropy of the reaction, whatever it is that you're looking at, plus the entropy of everything else that's not that reaction, that always increases. So that's the statement. Any spontaneous process, the entropy of the universe increases. You could come up with a hypothetical process that the entropy didn't increase in, but it's non-spontaneous. You'd have to somehow couple it to another process that is non-spontaneous. There's lots of non-spontaneous processes that happen on Earth, but that's because we're being driven by the energy from the sun, and there's a lot of entropy going on in the burning of the fuel, the fusion burning of the fuel of the sun. So lots of naturally non-spontaneous processes that decrease entropy are happening on Earth because of that large input of energy that corresponds to an entropy increase in the sun. Yes, so if we look at these cases, increase of entropy is spontaneous. It's an equilibrium. A process neither goes forward or reverse if the change in entropy is zero. And if there's some process that would decrease the entropy of the universe, it is a non-spontaneous process. It would need to be connected to a process that is spontaneous. Yeah, so an equivalent way of thinking about it, the universe spontaneously moves to more probable states, right? We talked about that in the last lecture, how increases in entropy have to do with molecules moving from, or systems moving from states that are unlikely to states that are more likely. For example, if you have all the gas on one side of a room and let it go, well, it's going to keep moving, and it's going to move towards states that in general have the particles on both sides of the rooms. You can get all the particles on one side of the room again, but what you'd have to do is exert some work to push them all over, put some sort of barrier in place to keep them on that one side of the room, and that would incur some effort that would actually increase the total entropy. It would increase the total entropy more than you decrease the entropy of pushing all the particles to the other side of the room. So there actually is a third law, and that is that the entropy of a perfectly ordered crystalline substance at 0 Kelvin is 0. So if we're at 0 Kelvin, perfectly ordered, not like carbon monoxide, we could switch the positions. There's only one possible state, and that therefore the entropy is 0. Yeah, so log of 1 is 0, there's only one state. And this actually gives us a reference for entropy. Absolute entropy does have a meaning where everything is frozen in place. Absolute enthalpy does not. There's no such thing as an enthalpy of zero. You can have an enthalpy change of zero, but the only thing that's really physically meaningful is changes of enthalpy. Interestingly enough, though, that yeah, you can have a zero entropy. It's when you know, as it shows right there, there's only one state possible. You're frozen in place. The entropy is zero. An interesting consequence that we won't prove why that's the case. It turns out you cannot cool a substance to absolute zero by any real world process. That ends up being a direct consequence of the third law, but we won't get into the proof of it there. But it's kind of cool that you actually cannot cool anything to absolute zero.